So this is question 11 from the component 3 A2 task booklet, and this is another nervous system question, and we've got a lovely diagram and then we've got a great table of stuff there. So the diagram shows how the resting potential is maintained. Now we know how the resting potential is maintained, but it's always worth having a look at the diagram. So what have we got? We've got the outside of the axon, we've got the inside of the axon presumably, so that's the axon cytoplasm. We've got a closed channel, we've got an open channel, and we've got a sodium-potassium pump, and we've got some proteins on the inside. And then we're shown this high concentration of plus, so that sort of gives you a bit of a starter for this. So first one, describe what is meant by the term resting potential. So what do you understand by that term? So resting potential, it's not that the neuron's doing nothing, obviously. Neurons never do nothing. So this is when there is no, so this is the potential difference, like that, potential difference across the membrane. When there is no action potentials. That's the key, isn't it? So this is the membrane just being, waiting for something to happen. We've got no action potentials going on. That's what resting means. It's not actually conducting anything. We're going to need to say something else because it's for 2 marks. So I'm going to say that the membrane is polarized. With the inside of the axon being negative. And I'm just going to put a value there, minus 70 millivolts. So what's the next bit? So part B. So that's just a quick, describe what you understand by that term. Next, explain how it's maintained. So how do we get it to be negative on the inside? And actually when I marked this you were really much better at this, although didn't give many 3 marks away. So not too many 3 markers here. So looking at the diagram, I'm going to do the sodium-potassium pump first. So sodium-potassium pump moves 3 sodium ions out of the axon and 2 potassium ions into the axon using ATP. So I'm just making it very explicit that I know that that is active transport. We've got a closed channel and we've got an open channel. The membrane is more permeable to potassium ions, so they diffuse out. But sodium ion channels closed. So sodium ions don't diffuse in. Now quite a lot of people told me that the potassium ion channels were leaky and let the potassium ions out, which is fine. And some people told me that the sodium ion channels only allow very slow diffusion in, and that is also fine. So what do we need now? We need a calculator, so I'll get my trusty calculator out because I can see already, I've not even looked at the top yet, but I'm going to have to calculate something there. Lovely, calculate. So, a little bit of information. Demyelination, loss of the myelin sheath, which occurs in some neurodegenerative autoimmune diseases, including multiple sclerosis. So I've got multiple sclerosis in the table as well, so that's clearly important. This condition damages, so this is where they're going to tell us what it does, it damages the myelin sheath in the brain, spinal cord, optical nerves. The reaction times of multiple sclerosis sufferers compared, so we're looking at reaction times, together with the percentage of correct responses, and the stimulus is visual. So, what we've got going on here is you've got the eye detecting the stimulus. We're sending an impulse down the sensory, because that's a receptor, sensory, into the brain or spinal cord, out down a motor neuron, and off to presumably a muscle. Doesn't really tell us what they had to do, does it? Just reaction times. Let's say, well, it's going to be a muscle then, isn't it? And of course everything in there is all the grey matter, so that's all non-myelinated anyway. So we're looking at the sensory and motor neurons, and the stimulus being visual. And what do I know? Presumably the optic nerve, which is the one that they've mentioned, is the one that goes from the eye to the coordinator. So we've got this stimulus receptor, sensory neuron coordinator, motor neuron effector thing going on again. So, okay, so we've got our group, we've got multiple sclerosis, we've got people without multiple sclerosis, we've got our reaction times, and we've got our correct responses as a percentage. Okay, so our calculation then. Calculate the percentage increase. So, how far it's gone up from having multiple sclerosis compared to a healthy individual. So, percentage increase means we need the difference between the two. 549 minus 443. And we're looking at an increase. What does it increase from our healthy number? From our healthy number, 443, it's increasing from that, times by 100. Pop the numbers into my calculator. 549 minus 443, that gives me the difference, 106, divided by what it's come from, 443, and then times by 100, and I get 23.927. So I'm going to put 23, and I'm going to round up that 7 to make it into a 3.93, and it's a percent, so put that in as well. It would be silly to lose units. So now I'm going to have to do something with it. Explain the difference. Give reasons why the multiple sclerosis results are take almost this quarter along. So I need to look back at the top now. So this condition damages the myelin sheath of the neurons. So what do I know about the myelin sheath? I know that if somebody is healthy, we've got saltatory conduction, and it's fast conduction of action potentials, and it's jumping from node to node. So if it's damaging the myelin sheath, then our multiple sclerosis sufferers won't have that jumpy. They'll be doing it the whole neuron, so all the neuron, and we're going to have no saltatory, and it's going to be slower. Now, it really doesn't matter which way round you do it. You could either have done it in a healthy individual, the myelin sheath means the action potentials only form at the nodes. This gives saltatory conduction, which speeds up the action potential conductance. I'm going to take it the other way round and explain what it means for somebody with multiple sclerosis. But because it's just saying explain the difference, it doesn't matter whether you take it from this or not, or that group. So, in people with multiple sclerosis, I'm going to abbreviate that to MS in case I need to use it again. And again, belt and braces, if you're going to abbreviate, use whatever you like as your abbreviations, but tell your examiner what it is an abbreviation for. So, the multiple sclerosis sufferers, the myelin is destroyed. Actually said damaged up there, I probably should have used that word instead, but anyway. This means the wave of depolarization, I always imagine it as a Mexican wave going down the axon, because along the whole neuron, I'm just going to make sure that they know exactly what I'm talking about now, not just the nodes. Okay. There is no saltatory conduction. So the transmission, I think you could use propagation there just as easily, of the nerve impulse and action potentials. Again, you know, they could acquire what they want, so sometimes they just like, you know, they're okay with you just using nerve impulse. Sometimes they want you to talk about the action potential propagating along. Is slower than usual. So I think that sort of covers it, and I think I've said 3 different things because I need to throw. I've got 3 marks here. So I've got the whole neuron idea. I've got mentioned this key term, saltatory conduction, and I've explained that it's slower than usual. So reaction time's longer. I'll put that in as well. Because, you know, you're not mind readers. Nobody is. So reaction time is longer. with MS. And I'm okay using MS because up here I told my examiner that's what I was using. Great. So, last mark, suggest. Oh, I love these. Suggest a reason for the decreased correct responses. So all of this has been about reaction times. Now I want to think, correct responses. We're not sure what the task was, so we don't know, whether it was sort of, press the green button when you see a light or press the red button or whatever it was. But the key thing for the information is to use this bit here. So it tells you it damages the myelin sheath of neurons in the brain. That'll be white matter, spinal cord, white matter, and optical nerve. And of course it could be, because we're in the brain, it could be a sensory neuron, which of course is myelinated and therefore is part of the white matter. So, correct responses, it's obviously that something's not getting through to the brain from the stimulus through the eye. So, decreased correct responses. The damage to the sensory neuron and optic nerve. I'm just going to put hinders detection of visual stimulus. As we know that the stimulus was visual because it said so up here. Okay, hope you did alright on that one.